Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And hi, my name is Siti binti Zainal and my matrix number is 1190909. So for today, I will explain about one of the applications of eigenvalues and eigenvectors. Before that, what is eigenvalues and what is eigenvectors? Eigenvalues. Eigenvalues are often introduced in the context of linear algebra or matrix theory. It has the greatest importance in dynamic problems in the study of engineering. Eigenvalues are scalars that is used to transform, whether stretched or compressed, an eigenvector. An eigenvector is the vectors. The vectors that when a linear transformation, such as multiplying it to a scalar, is performed on them, the direction does not change. The formula that we can contribute in this is AX equal to lambda X. It means the scalar lambda is called an eigenvalue of A, and the non-zero vector X is an eigenvector of A corresponding to lambda. The multiplication of a matrix A changes the direction of the vectors X in A. However, certain vectors will still be in the same direction. That is what it means by this formula. Both eigenvalues and eigenvectors have various applications. They play a major role in the study of ordinary differential equations and in many applications in the physical sciences and engineering, such as we can apply the eigenvalues and eigenvectors in the stability analysis, vibration analysis, facial recognition, matrix diagonalization, and what I choose is atomic orbitals that I choose as hydrogen. So without further ado, we begin with the hydrogen atom applications of eigenvalues and eigenvectors. Before that, we know that hydrogen atom has a system which hydrogen atom consists of a proton of mass mt equal to 1.7 times 10 to the power of negative 27 kilogram, and its charge q equal to 1.6 times 10 to the power of negative 19 coulomb, and an electron of mass me equal to 9.1 times 10 to the power of negative 31 kilogram and charge negative q. Consequently, they are bound by a coulombic potential, which we can say Vr equal to negative q squared over 4 pi E naught 1 over r equal to negative E squared over r, where permittivity naught is the permittivity of free space. From that, we get the classical Hamiltonian of hydrogen atom, which is HRP equal to P squared over 2 micro minus E squared over R. So from the Hamiltonian formula, then we can perform the finding of eigenfunctions and eigenvalues of the Hamiltonian, which it will become like this. Then about this whole thing of hydrogen atom eigenvalues and eigenvectors, the energy levels or the energy eigenvalues En of the hydrogen atom depend only on n, which is called the principal quantum number. Since the energy levels and radial decay rate depend only on the n number, This number is used to identify an electron shell. For each energy En, there exists several values of L, which is L equal to 0, then n minus 1. This means that there are more than one eigenfunctions for each energy eigenvalue with different angular momenta. These are called subshells. Then, to each value of L correspond to L plus 1 values of M, which is M equal to negative L, then negative L plus 1, then L minus 1, then L. Each subshell contains, which is 2 L plus 1 eigenfunctions or states. The levels of En are n squared degenerate, which we can say, which is sub L equal to n minus 1, L equal to 0, 2L plus 1 equal to n squared. The eigenfunctions common to L, Z, L squared, H, U, and Lm are theta and P are completely defined by specifying three numbers, which are called quantum numbers and Lm. The angular dependence of the eigenfunctions is determined by the spherical harmonics Ylm theta P. Since the P dependence goes away upon squaring, one can plot a projection of the eigenfunctions onto the zx or zy plane. The plots are surfaces of revolution about the z-axis. The asymptotic behavior of the radial function are near the origin or are almost to RL. Only eigenfunctions U, A, 0, 0 are theta P belonging to S subshells have a non-zero probability of being near the origin. The spectroscopic notation assigns a letter to each subshell. N equal to 0 to S, L equal to 1 to P, L equal to 2 to D, L equal to 3 to F. And then we can compare this energy level, which is energy eigenvalues, spacing in free particle, and then 1D box, and then 1D harmonic oscillator, and then also in hydrogen atom, which we can see in the 3 box below. Do these eigenvalues and eigenvectors in a Python also. How to calculate this in Python? First, we know that we must use the numpy. First and foremost, import the numpy as np. From numpy, import lin algebra as LA, linear algebra as LA. Then input. The input we can use as equal to np dot array. We can put the inputs there, and then we can get WV equal to LA, the linear algebra, again, and the input. And then for the conclusion, we know that the conclusion for the eigenvalues and eigenvectors are only defined for square matrices. The diagonalization of n times n matrix AE is important, particularly in finding a basis for Rn that consists of eigenvectors and for simplifying various numerical computations. The diagonal matrix of D equal to P power of -1 AP can be found easily by substituting the diagonal entries of D with the eigenvalues of A. And that's all from me. Thank you.